So, given each of these functions, again, I'll think of this one in green and this one in blue, and being able to remember what these graphs look like is very helpful. So again, that's a review of chapter 1 and chapter 3 with the transformations, and chapter 2 with rational and radical functions. So 1 over x plus 3, you might see that there is a non-permissible value at -3. You might see that the degree is bigger on the bottom. So you could use chapter 2 to graph this one. Find two nice points, including your y-intercept at 1/3, and you have your graph. You could also, if you think way back to February, 1 over x was one of our parent graphs. And this is just the 1 over x graph moved 3 to the left. If, this is not good. That was supposed to be in green. Well, that's pretty good. That was our green graph. Now our blue graph is a parabola. Probably if I would do this parabola, I would use some skills from grade 11. I would factor it, and by factoring it, I would find that my two x-intercepts are at 0 and 4. I'd also see this parabola is a positive x squared, so I would know that it opens up. If I wanted to, I could plug in 2 and find my vertex at 2, -4. So we have lots of graphing skills. And I'm going to tell you, you're going to need all of these graphing skills really, really well for calculus. You want to have all of your graphs memorized and easy to work with. So you see these, you can graph them quickly and easily, because that's going to really help you in your calculus course if you're taking it next year. So in A, now it says determine an explicit equation, then state its domain. So if I want to write g of f of x, one thing I just want to highlight, because they lose so many on the final exam and on quizzes and tests, students lose so many marks because of this word. If something wants you to find an equation has an equal sign, and it has something on both sides. So we can't just write g of f of x on its own without an equal sign. So by wanting the equation, I have to have an equal sign. I have to have something on both sides. So y equals g. F of x was the green one. That is, right? F of x was my green function. It can get replaced with the function 1 over x plus 3. And now g of x says whatever you get gets squared, and then you minus 4 of that. So I'm going to have 1 over x plus 3 getting squared. And then I'm going to subtract 4 of 1 over x plus 3. What is the domain of this? Well, does this look like something you've graphed ever? No. So we might not be able to graph it. But we can still figure out the domain just from the equation, because the domain is asking, what are your possible x values? In your calculator, is there anything you would plug in that would cause it to say error? Yes, right? Because we can't divide by 0. So we know for sure that x can't equal -3. Is there anything else that would cause it to have an error? Or could you plug in any other number? We don't have any square roots here, right? Because you can't square root negatives. You can't divide by 0. I guess you've learned some new stuff. Like you've learned you can't take a logarithm of a negative. or the logarithm of 0. But there's no logarithms in here. There's no square roots. So this is the only restriction. X can be everything else. On the exam, if you just write x can't equal 3, they'll be fine with that. If you want to put a comma and say x can be everything else, that would be fine as well. Okay? B. We're going to do f of g of x. Well, g of x was x squared minus 4x, right? G of x was our blue function. It was equal to x squared minus 4x. And then f says, whatever you put in, we do 1 over that, so x squared minus 4x, and then add 3. So this is our explicit equation. This is one you did, though. You graphed this. We graphed this in chapter 2. This is a rational function. What did we do in chapter 2 with rational functions? We factored first. Can we factor the bottom? Absolutely. X minus 3, x minus 1. It has non-permissible values. So what is the domain? X can't equal 3, and x can't equal 1. And those would be holes or vertical asymptotes. All right, this oh, we may as well. Looks like it would be so much fun to graph. So we may as well graph it. You would have at 1 and 3 vertical asymptotes. Remember that? And then since the degree is bigger on the bottom, you would have a horizontal asymptote at 0. You could easily find your y-intercept. Oops, not there. At 0, positive 1/3. And since I have that point in this section, that turns nice. Can you see that there is no x-intercepts because your numerator is 1? I would plug in 2 to see what I would get as a nice point. If I plug in 2, I get negative 1, which would be enough to tell me this section looks like this. And then I would plug in 4, and if I plug in 4, I get 1/5, which is enough to tell me this section looks like this. There's the graph. Its domain is everything except x can't equal 3 and x can't equal 1. So I wanted to do one of the questions from the homework together with you. And that is 6D. You can circle 6 because I'm gonna assign all of 6, but we'll just do 6D together. We want an explicit equation for y equals f of x. Again, it wants an equation, so I need an equal sign on both sides. And f of x happens to be 1 over x minus 1. Because that is, here we'll make f of x green. So I'm replacing that f of x with 1 over x minus 1. And now the 1 over x minus 1 goes back inside of f. And the rule for f is whatever you put in, do 1 over that thing that you put in minus 1. I'm putting in a fraction. So I'm going to have, and this is why I wanted to do this one together, I'm going to have 1 over, and then I put in 1 over x minus 1, and then u minus 1. So we get a fraction put into another fraction. And one of the reasons I wanted to do this together is because if you left your answer like this, a fraction inside of a fraction is called a complex fraction, and you lose a half a mark for not simplifying. You don't have to simplify fractions if they're a fraction, but they don't allow you to keep fractions inside of fractions. So this is sort of a review of identities. Because identities, you had lots of fractions inside of fractions, and we had to simplify them to a single fraction. How did we do that? Well, what we did was we got a single fraction on the top, which it was 1. I can write it as 1 over 1. And on the bottom, I got a single fraction as well. Well, if I want to put these together, I need a common denominator for subtracting. So I'm going to multiply the other one by an x minus 1. So I get a common denominator of x minus 1. Careful when subtracting. Notice I kept this in brackets because this is subtracting all of that. So it's going to be minus x and then plus 1. Then, if you have a single fraction on the top, which we do, and a single fraction on the bottom, which we now do, a fraction divided by a fraction is the same as multiplying by the reciprocal. And this bottom will be negative x plus 2. So our explicit equation is just y equals x minus 1 over negative x plus 2. And I also wanted to do this one. Okay, we did this for D. It says to do the domain. And there's another common mistake. I'm going to make it right now, and then you tell me what mistake I made. I'm going to write the domain. Well, we can't divide by 0, so x can't equal 2. That makes sense? Because domain says, look, if there's any x values that you're not allowed to do, and we can't divide by 0, so x can't equal 2. I made a mistake. Looks right, doesn't it? That's the mistake. There's another non-permissible value that's hidden. X can't equal 1 either. But 1's allowed to be 0 in your numerator. Why can't x equal 1? Well, I'm going to take out my highlighter. Well, maybe. I'm feeling bright blue today. Sun is shining. We're dividing right here, right? Is there anywhere else in this equation that we divided? Oh, we divided there. We also divided there. And we also divided there. We have to look everywhere that we divided in the whole equation. And if initially 1 wasn't allowed, right? You gotta think back to your garage where you had 2 machines. This one machine is at, this machine is at. If you put a 1 into the original machine, not happy. Plugging a 1 into that original machine would make it blow up. It wouldn't even get into the machine, right? What we found with the explicit, when you get the explicit equation, this explicit equation, that would be like you went out and bought the new super machine that does both at once and no longer has a problem with the negative 1. The new super machine, you could plug in, with positive 1. The new super machine could take a positive 1, no problem. But the old composition machines says, well, what are we actually doing? We're putting it into 1 first, and then we're putting it into the second one, and we have a problem with putting the 1 into the 1 first. So this is another reason I wanted to do this one together with you, Because how easy do you see yourself looking just at the end and doing the domain? And saying, oh, x can't equal 2. But you have to check everywhere to make sure there's no other restrictions earlier on.